Hey everyone, it's Ferrari, a math class, and we're here to talk a little bit about antidifferentiation by parts or integral by parts. Depending on where you come from, you might call it a different thing. And well, this is a place where a lot of calculus students really start to feel overwhelmed because there are a number of things here which seem really nebulous. So I'm going to try to dispel some of that in the next couple of minutes. And let's get started over here. When I start with my students on antidifferentiation by parts, I really like to think about, well, where does this all come from? And right over here, it really comes from the product rule from the derivatives. So if you remember the product rule of the derivatives, if you take the derivative of a product, that's the derivative of the first multiplied by the, no, I'm sorry, that's the first function multiplied by the derivative of the second function plus the second function multiplied by the derivative of the first function. Okay. So that's not really that big of a deal. Let's take a look at those blocks and do a little bit of algebra here. So in this case, we're going to subtract from both sides the v du dx from both sides. So if I do that, I get this term right over here, which we're going to rearrange, and we get this term, the derivative of uv minus v multiplied by the derivative of u. And if you don't see it, this is the basic setup now, because all I need to do is take the derivative of everything with respect to x, and the derivative of everything with respect to x, we get, sorry, the integral of everything with respect to x. Well, the only piece that really simplifies is this one right here. If I take the integral of the derivative of uv, I just get uv back. And everything else just kind of simplifies into this integration by parts formula. So the integral of u dv minus uv, sorry, the integral of u dv is equal to uv minus the integral of v du. So this is the big formula. Comes very directly from the product rule for derivatives. Looking at the right side over here, the mnemonic device that a lot of people use here is ultraviolet voodoo. So if you see ultraviolet, that's the ultraviolet part. And the voodoo part is this right here, voodoo, ultraviolet voodoo. So I tend to use the words ultraviolet voodoo to mean integral by parts or antiderivative by parts. It's just a whole lot easier on my mouth to say. So when you hear me say ultraviolet voodoo from now on, it's integral by parts. Okay, so we're going to integrate this one right here with integral by parts. So here's our step by step. First of all, really important, make sure that all the other methods fail. Okay, integral by parts is kind of a measure of last resorts. So IVP is a last resort measure. Last resort technique, I should say. Okay. If you can use a substitution method, don't bother with integral by parts. Okay. If you can just find a way to simplify the integrand, then don't do integral by parts. It's not, well, if you use it where you don't need to use it, I find that most of my students will get caught up in all of the integral by parts method and will make a mistake eventually. So it's a good way to get a problem incorrect if you use it in a place where it's inappropriate. So the first real step here is to choose u, or sorry, that should be a u. Choose a u and choose a dv. So our choices we have to make sure that we span this entire integrand. So looking at this integrand, I've got x, and I'm going to use that as my choice of u. And I have the other part here, e to the x dx, and I'm going to use that as my choice for dv. So when you put them together, this entire integrand is either part of u or part of dv. And maybe what we should say is these are factors. Okay, these are things that are multiplied together. So one factor is u, the other factor is dv dx. Okay, once we've chosen that, we're going to take the derivative of u, which you'll see over here, the derivative du dx of x is just 1. So we get du is equal to dv. So I'll write that over here again. Du dx, the derivative with respect to x of u, is equal to the derivative with respect to x of x. And that just gives me du equals dx. On the other side, we're going to take the antiderivative. So the antiderivative of dv is equal to the antiderivative of e to the x dx. Of course, the antiderivative of dv is v, and the antiderivative of e to the x is e to the x. And we're going to ignore that plus c for now. It's going to be there, but it's going to be kind of there in the background. So we've created 4 different blocks here, 4 different things. And we're just going to substitute them in. So the first one that we see is u, and whenever we see a u, we're going to substitute our x. The next part is our dv, and whenever we see dv, we're going to put in our e to the x dx. Here's our dv, here's our dv, and I think that's the only place where we have a dv. The next thing we have is our du. So if I see in the ultraviolet voodoo formula du, I'm going to replace that with dx. And then the last thing in our formula is the v. So whenever I see v, I'm going to substitute that with e to the x. So all of the blocks are in place, and we can rewrite this as the integral of x e to the x dx is equal to x e to the x minus the antiderivative of e to the x dx. Okay. Didn't really do a whole lot here, just did a little bit of the algebra work. And then now looking at this integrand, this is actually easy to do. We know what the antiderivative of e to the x is. It's x e to the x minus e to the x plus constant. Okay, and that's what we get over here. So what happens in integral by parts is what we trade in, once we trade in one integral, which is the one we started off with, we trade that in for this integral over here. And in the process of doing that, we create a little bit extra, another term. So in going from here to here, we have to make sure that our integral kind of simplifies. And the way to do that is to make sure that when we take the derivative of u, the derivative of u must simplify things, must be simpler than u. It's that simplification process that allows this second integral here to be integratable. Let's take a look at this problem over here. we've got x cosine x dx, and it says hint u equals x, but let's kind of not look at that hint for now, and let's just think, what can I use for u? And remember, the factor that you choose for u should be something that simplifies as you take the derivative. Now, if I say u is equal to cosine x, if I take the derivative of cosine x, that derivative is negative sine x, and that doesn't really simplify things. So the other choice is to use x. So let's see. We're going to use x as our u, and we'll use cosine x dx as our dv. So step one, let's make sure that all of the methods are going to fail. And looking at that, that's the product. There is no product rule. There's also no trig substitution I can use to make cosine x, simplify or go away. There's no substitution I can use for x cosine x. That's certainly nothing that I've learned in trigonometry. So really, I'm kind of at a impasse here. There's no way to simplify this. I can't use a basic technique. If I decide to use a substitution, well, what am I going to substitute? I mean, if I substitute u equals x in the substitution method, that's kind of treading water. So we are now at integral by parts. So part 2, choose u and a dv, and I think I've already said u is going to be x, dv is going to be cosine x dx. Step 3, so that's our step 2. Our step 3 is to take the derivative of u. Okay, so du dx is equal to 1, so du is equal to dx. Once you do a lot of these, you're going to start automatically putting the dx on the right side here, multiplying it through. So just get a little bit used to that. Du dx, just put the dx on the right side of the equal sign. And then we're going to integrate here, so v is equal to the integral of cosine x dx, which means that v is equal to sine x. Really, there's a plus c here, but we'll just kind of ignore that for now. Or you know what? Let's just go ahead and put that in there. Nah, we'll do that later. Okay, so here is our antiderivative. Step 4, we're going to substitute into ultraviolet voodoo, and I'm going to write the formula out, the integral of v du, u dv is equal to uv minus the integral of v du. We'll put our blocks in place. U is x, dv is cosine x dx, equals u times v, u is x, v is sine x, minus the integral of v, which was sine x, multiplied by du, which was dx. Look how nicely that worked out. Setting u equal to x, once I took the derivative of x, I'm really left with nothing but that dx. That's a heck of a lot simpler than whatever we started off with. So we'll do a step here. Let's color code these things for you. Okay, so that looks nice. And do some algebra to clean it up. Minus the integral of sine x dx. And what is that antiderivative of sine x? Well, that's just equal to negative cosine x. So this is x sine x minus negative cosine x plus constant. And that's our antiderivative by parts. Of course, you can simplify this part over here algebraically, but I'm going to let you do that on your own. And here's some wisdom about integral by parts. So number one, really important, we talked about this already. Make sure that all the simpler integral methods are not possible. They don't lead to an antiderivative. Make sure that your choice of u and dv covers the entire integrand, including the dx. Really important here, otherwise you're just kind of doing a half measure. So do the entire thing. The entire integrand needs to be either part of u or part of dv. U needs to simplify every time you take a derivative. And polynomials and logarithms are particularly good choices for u because as we take the derivative of those, they get simpler. dv, whatever you choose for dv, needs to be something that is integratable. Otherwise you get nowhere. And lastly, and this is the part that most of the students wait for or wish they know, is that there's an acronym, LIATE, that's, I estimate it to be about 90% accurate. Okay, and this is helps you choose u. So the first thing, your first on your list is logarithms, because we can't really take an integral of a logarithm. So we put that as our choice for u, because we can take the derivative of logarithms really easy, but their integrals tend to be troubling. Same thing with inverse trig functions. The derivatives are pretty straightforward, although, not that straightforward, but more straightforward than their antiderivatives tend to be. The next, and this is the choice that we're going to use most often, is the algebraic function, which basically means a polynomial. So anytime we see a polynomial, that's a good choice for algebraic functions. And I find that that's, the algebraic piece as a choice for you. That goes for about 70 to 80%, maybe even more, of the functions that you're going to see. You're going to use the algebraic function or the algebraic factor as your choice for u. Moving on down, you have trig functions and then exponential functions. Exponential functions and trig functions are last because most of the time, if you take the derivative of a trig function, you're going to get another trig function back. I shouldn't even say most of the time. I should say every time you take the derivative of a trig function, the derivative is going to have another trig function in it. So it doesn't really simplify things. Same thing with an exponential function. If you take the derivative of an exponential function, you're going to get another exponential function out of it. So it doesn't really simplify things. Remember that this is an ordered list. So start at the top, move down to the bottom, and we're going to take a look at this right here. So number one, let's see. Find the antiderivative of this function here. I'll color the factors here. And let's decide right now, of those two factors, which one's going to be u and which one's going to be part of dv. And x squared is algebraic, that is a polynomial. Natural log of x, well, natural log is a logarithm. So going back to Liate, L comes before A. So my choice for u is going to be the natural log, which means that x squared dx is going to be my choice of dv. After you choose your u and your dv, you're going to take the derivative of u and the antiderivative of v. At this point, a lot of you are going to start taking the antiderivative basically just in your head. And that does lead to a lot of mistakes because, we haven't been with antiderivatives for so long now that, just going through it as like it was a basic function is not something that comes automatically to us yet. But this is where a lot of students pick up their fluency with antiderivatives, is trying to get these antiderivatives really quickly so that they're not on the same integral by parts problem, for 10 minutes. You don't want to do this problem for 10 minutes. It's not that difficult. So here's our full chart. I like to look at this as, when I see it, it looks like a two-line, two-row table to me. And that kind of helps me because if I take the antiderivative, I just go diagonally over here. So natural log times 1/3 x cubed minus, and then we go across that way. Now that we have it all written out, we're going to simplify. Notice how right over here, that integrand is actually really easy, or is greatly simplified, and it's only greatly simplified because we chose our u to be natural log of x. So the derivative of a natural log function basically gets rid of the natural log. Not basically, it gets rid of the natural log. So that simplifies things greatly. And then from here, whatever happens is going to happen, but you're not going to have that natural log to deal with anymore. So as our last step here, we're going to take the antiderivative of 1/3 x squared. As it turns out, that's not a really difficult antiderivative anymore. It's usually customary to do a little bit of factoring here, and if I take a look at the denominator, or the two fractions here, I'm going to pick the least common multiple of 3 and 9, which is 9, and I'm going to factor that out. So 1/9 I'm going to factor out. Taking a look at the x's, I'm going to factor out the highest ordered x. These are of the same order, so I'm going to factor out an x cubed. Okay. 1/3 divided by 1/9, that's the same thing as 1/3 times 9, which is 3. So this is now 3 natural log of x, minus 1/9 divided by 1/9 is 1. 1/3 divided by, x cubed divided by x cubed is 1. So we just get a 1 here. Then our plus constant. Make sure when you're factoring you don't put that plus c inside the parenthesis here, because that is kind of flat wrong. Okay, looks pretty good. Let's move on to letter B, and the hint here is that you're going to have to use ultraviolet voodoo twice. Okay, let's use ultraviolet voodoo twice. Let's start by color coding our factors here. Our first factor is x squared. Our second factor is e to the x. And we need to decide which of those two factors is going to be our choice for u. X squared is algebraic. E to the x is exponential. Algebraic comes before exponential in Liate. Liate. So it looks like my u is going to be x squared, which means that my dv has to be everything else, which is going to be e to the x dx. Okay. Notice how I kind of waited until the very end to decide, does the dx go with e to the x, or does the dx go with x squared? You probably notice I did it on letter A also. Okay, and the rest of this, let's just keep chugging along here. Let's take the derivatives and the integrals. If you see things really visually, you've probably noticed, again, how this is kind of a 4-quadrant thing. And so the pattern here would be to go down that way and then across that way. Okay, and now that you've put all the blocks together, you're going to go ahead and simplify this. And looking at the integral that we've created over here, I notice that I have to use integral by parts again, which is not that big of a deal, really, but I think in order to keep the algebra straight, I'm going to go ahead and put all of this inside a nice big bracket so that this minus sign over here doesn't play tricks on my algebra. Okay, inside my big blue bracket, we need to pick our 2 factors, and the 2 really can go with either the x or the e to the x as a kind of a principle, or the way I normally do things. I try to keep that, any constant factors, I try to keep that with my algebraic function. So my 2 functions here are algebraic, 2x, and exponential, e to the x, which means that my choice for u should be 2x, algebraic, and my choice for dv should be e to the x, which is my exponential. That means that this dx part needs to go with dv. Okay. Rinse and repeat here. We're going to take a derivative and an integral. And with the derivative and the integral, now you should see again the 4-quadrant map showing up here. And you're going to go across in the pattern. If you are a visual person, that's really what you would do. And let's put this all together again. Notice how, because this is a subtraction over here, it's really easy to forget to distribute that minus across all of the factors here in blue. And yeah, this looks pretty good. Let's simplify. Over here, the integral of 2e to the x, that is not bad at all. That is just 2e to the x. From here, we're going to factor. We notice that in the first 3 addends, we have an e to the x, so we'll factor out that e to the x, which completes the problem here. Sometimes what you see inside this parenthesis, that may or may not be factorable as a quadratic, but not really necessary in a calculus class to factor that out. So here's our antiderivative for the second one, and this brings us to what are the important details here for antidifferentiation by parts. So integral by parts is a way to simplify integrals that, that come from a product rule, really. So it integrates a derivative from a product rule. By itself, it is not a product rule. A product rule would mean that for every product, this is how we integrate it. This is just how we integrate some products that we see in the integrand, 2 things being multiplied. So we have the steps laid out for us again. Make sure that all the other methods fail. Choose your u and your dv. That should be a u. Differentiate u, integrate dv, and then substitute into the ultraviolet voodoo formula. Now, the Liotte that we see over here, this is just a way for us to remember what to use, what to choose for u. And it's an order of preference from most to least. So logarithmic functions, definitely make that u if you see any. Inverse functions, algebraic functions, which is the most common. And then if you see none of those, then you go to trig functions and exponential functions. Here's our check your understanding. Hermione Granger, perhaps one of the finest witches in her generation, attempts to conjure butterbeer. The rate at which butterbeer appears in her cauldron is given by RT equals x squared e to the negative x liters per minute. So how much butterbeer does Hermione conjure in the first 4 minutes? T equals 0 to 4. And if we're given a rate, liters per minute, if you integrate that rate, then you're going to get the total amount of liters. So let's integrate x squared e to the negative x dx, and that's going to, from 0 to 4, that's going to give me liters. Okay. So the strategy here, if you're going to be using definite integrals, the strategy here is to start with the antiderivative. So we're going to break down this problem into steps here. Okay, so this is really similar to the problem that we just did previously, and you'll see a lot of the same things. So we'll start off by color coding and taking a look at our two factors, excluding dx for now. And we'll say, well, which of those two is higher up on the order for u? And higher up is the algebraic part, x squared. So dx is going to be part of the dv part. Okay, and we'll set up our quadrant thing again. U is equal to x squared. dv equals e to the negative x dx, which makes du equal to 2x dx, and v equal to, now be careful with this negative sign right here. Okay, when you take the antiderivative here, that's going to have to be negative e to the negative x. And for some of these, sometimes you don't even want to think about the antiderivative. You just want to think about, well, what would I need to take the derivative of to get e to the negative x? So sometimes that works better, I should say. Set this up again, and you're going to multiply down diagonal, and you're going to put the across diagonal here into the integrand. Okay, substituting into ultraviolet voodoo, we get uv is x squared multiplied by negative e to the negative x minus v du, so the integral of negative e to the negative x multiplied by 2x dx. Simplify. And of course you find that this integral right here is actually, in order to integrate that, you'll need another instance of integral by parts. So let's do the same thing that we did previously. We're going to color code our two factors, 2x and e to the negative x, and we're going to decide which of those two is higher up on our preference list. 2x is algebraic, e to the negative x is exponential, so 2x is going to be my u, which means dx is going to be part of e to the negative x. Set up our quadrant. U is 2x and dv is e to the negative x dx. Derivatives and integrals. By now, we should be familiar that the antiderivative of e to the negative x is negative e to the negative x, And then we're going to set this up again and put together our second integral by parts. Okay, putting in all of those integrals, or putting every piece in here. It looks like we're running out of space, so we'll just move up to the top. And we'll simplify it up there. What do we have? We have that's equal to negative x squared minus 2x e to the negative x. And I forgot something here. Okay, negative x squared e to the negative x minus 2x e to the negative x plus the antiderivative of 2 e to the negative x. Moving that to the top of my paper, now we just have to take the antiderivative of 2 e to the negative x, which is just negative 2 e to the negative x. Okay, plus constant in the back. Let's group all of the non-constants and let's see what we can factor. 1, 2, and 2. It doesn't look like there's anything to factor there. But each of these terms have an e to the negative x, so we'll factor that out. And we also see that each term is negative, so it might be easier if we factor negative e to the negative x, which is the same as 1 over e to the x. This, I think, is preferable because I don't like my final answers to contain negative exponents. And when we factor negative e to the negative x from every term in the parenthesis, we get x squared plus 2x plus 2. So this is our antiderivative. The antiderivative of x squared e to the negative x dx is equal to this thing, which means now we can do our definite integral really easily. It's just our antiderivative evaluated at 4 minus our antiderivative evaluated at 0. Substitute those quantities. Now, don't take for granted that when you substitute 0 in this second term that you're going to get 0. In fact, you get 2. And let's simplify this one more step, and then we have our amount of butterbeer. So we get Hermione Granger conjuring about 1.5 liters worth of butterbeer during those 4 minutes. How about we get an average rate? So this is going to be our part B. Our average rate, that's just going to be 1 over 4 minus 0 multiplied by that same integral, the integral of the rate. And, that's just 1/4 of 1.52379. And then now we do liters divided by minutes. So it's liters per minute. And, you can calculate that, of course. That's not that difficult. But that's the end of it. Yeah. So hopefully that works for you. This is a subject which you really need a lot of practice in order to really get good at. So I highly recommend, do as many of these problems as you can. Don't just wait for your teacher, if it's me or if it's someone else. Don't wait for your teacher to assign you, if you get 12 problems assigned, you're really better off doing 20 problems or 30 problems or as many as you can get your hands on. Trust me, there's a lot of material out there for you to practice integral by parts. So with that little bit of wisdom, I'm going to sign off, and good luck with your integral by parts. We'll see you for part 2 soon. Have a good one.